Welcome students, welcome to the lecture number 5. As we discussed, we are going to talk about materials and the structure in this lecture, and obviously carry forward what we have done in the last one. And I already talked about the fact that every lecture has two parts, each about 25-minute duration, but they are connected. Nonetheless, it is made such that you can follow them at your own pace. You can easily watch a 25 minutes video and pause and watch the next one whenever you want. That is what the purpose is. So, this lecture we will first discuss about what we have learned in the last lecture, so that you do not forget. That is what the basic aspect of this. But you know, many of these topics which I am covering will be available in the basic standard books on materials, structure, properties and processing. You can pick any of these books and read from them. So, basics of material science engineering is this correlation between processing, structure and properties. And you know, by processing it means the techniques which you use to make certain material. It can be simply liquid to solid, that is called casting. It can be deformation processing, it can be powder metallurgy, or it can be thin film events. Many kinds of processing techniques are available in the literature, and each of these technique has its own merits and demerits. Based on the processing technique, the microstructure or what you call a structure develop in the material, and this structure is what is important to determine the properties of the material. So, therefore, we need to understand these connections, and you know, you must be thinking why I am talking of these aspects in a course on machine learning and artificial intelligence. Well, at the end of this course, what you are going to do is to design materials, predict material properties. So, unless and until you know the basic aspect of those, how you can correlate them. So, there will be no correlation between the basics of materials engineering with the applications of AI/ML. That is why this needs to be done at the beginning of this course, so that you can actually understand it, and whenever you develop the various kinds of models for machine learning, you will be able to use this kind of fundamental concepts and models. So, fundamental aspect is the correlation between structure and properties, as we have discussed. What is the meaning of structures? Structures can be atomic structures, structures can be crystal structures or microstructures. As you know, when you see any component which is available in the world, what you see is a macrostructure, how they look like. But inside a microstructure, we can see even microstructures under a microscope. That is why it is called a microstructure. But if you still go down the dimensional scale, you can go to crystals and atomic pieces. And what are the properties we are going to discuss? Obviously, mechanical properties the most important, physical, magnetic, electronics, electrical properties is possible. You will expect to get a full understanding of this correlation between the structure and the properties. That is what is the main objective of these things. So, in a nutshell, we always deal with different kinds of materials. We want to discover new materials for different applications which are upcoming with certain target properties, and this is controlled by the basically processing and the synthesis conditions, the structure of the material. So, in a very philosophical way, the materials engineering uses the resultant knowledge of material science as well as engineering, both the aspects, and the resultant knowledge of the structure and the correlation of the structure of the properties, which in turn determine the performance of the materials, is what is the basic aspects of material science. Now, this has been done for over the last 200 years or so, and most importantly last 100 years we saw a lot of engineering aspects came into picture. So, we have to put it together in one basket, that is the idea. But first and foremost thing, I told you that in the materials world we have 4 different types of things. Basically, one is metals or alloys, ceramics, polymers and composites. They are mixture of these 3 or either of these 2 of these 3, okay. And their chemistries are different, obviously everything is different, properties are different, and even they have, some of them have very distinct properties which are not available in other cases. Like in the polymers, we have ability to process very easily, which is the basic characteristic of polymer. That is why you see so many polymeric products in the market today. But nonetheless, each of these species is very important. As far as the composites is concerned, they are easily available in the world. There are many natural composites available, we know that. The horn of rhino is a composite, and that is why it is very strong. It is basically a nanocomposites and nanoparticles inside a polymeric material, that is why it is biopolymer, that is why it is so strong. And composites can be a mixture of any of these three: metal and ceramics, metal and polymer and ceramics. We have all discussed about it. So, but basic structure of material is atom, that is why everything begins. But we have, if you want to understand electrical and magnetic properties, we have to go down in electronic structures, which we will see sometime later. But at the beginning, it is important to know that basic structure of material is atom, and that is why in a periodic table we divide the elements in a very nice way. I talked about it. The left side you have metals, central part also you have metals. You can see at left side you have metals, these are the metals, and then you have central part also metal. On the right side basically you have metalloids or gaseous presence. Metalloids like germanium, silicon, arsenic, antimony, tellurium, bismuth, they are present on the right side. And then you have this gases like fluorine, chlorine, bromine. Bromine is a liquid, iodine is also liquid present. But we have oxygen, carbon, nitrogen, boron, phosphorus, sulfur also present on the right side. That is why it is on the right side of this periodic table. And based on the arrangement of the atoms are basic building blocks. Now, how we arrange depending on the arrangements, you can have two types of structures: crystalline and non-crystalline. In crystalline structure, atom arranged in a very orderly manners, and non-crystalline structure atom arranged in haphazard or random manner. So, we will talk about non-crystalline structure later. So, when your atoms are arranged in a very nicely regular recurring way in a three-dimensional space, we need to know what is the unit which is getting repeated. That is what is the basic geometric group, and it is known as a unit cell. We already talked about it, and this pattern can be repeated million times in the three-dimensional space. That is why it gives you the whole crystal repeatability, and this is true for everything. It's true for metals, true for ceramics, and true for also some of the polymers. Well, the basic structures are divided into basically four different types. In a cubic system, there is simple cubic, there is only one atom each corner of the cube unit cell, and there is only one metal which shows this structure is called polonium. Then you can also have body centered cubic structure, face centered cubic structure, diamond cubic structure. Body centered cubic structure have, in addition to the corner atom, they have a center atom at the center of the unit cell. Face centered cubic structure have the atom at the faces of the unit cell. There are 6 faces, there are 6 atoms other than, in addition to the atoms at the corners. Diamond cube is different. It has atoms at the corners of the cube as well as the face center of the cube as well as at the voids, that is the tetrahedral voids within the unit cell. We already talked about it, like this atom which is at a tetrahedral void. You can easily draw a tetrahedron like this. So, within this tetrahedron you have this atom present. So, you can take away this tetrahedron very easily, and you can actually see that this tetrahedron actually is forming a hole inside it, okay, and this is the tetrahedron. So, inside this atom exists. So, diamond cubic or silicon, germanium or diamond has diamond cubic structures. You can also have hexagonal structures. I discussed about one major example is magnesium, titanium, zinc, aluminum oxide, Al2O3, alumina as hexagonal structures. And these are the examples of different metals which forms these crystal structures. BCC has chromium, iron, moly, tungsten. Face centered cubic structures aluminum, copper, many of the important metals like gold, lead, silver, nickel. And hexagonal crystal structure is magnesium, titanium, zinc. So, now once you arrange these crystals in a different way or basic way, you form microstructure. That is what is shown here. These are the different crystals, or they are called grains actually, we have written, and between the two grains you have boundaries. And once you see in optical microscope, you can see this kind of structures which is shown on the right side with iron grains at the boundaries shown by the lines of the curves like that. So, a microstructure can vary based on the pure iron or steels, we know that. Pure iron has no other elements, but steel has about 0.8% or less than that of carbon, and this can lead to carbide. We have basically mixture of iron plus carbide. That is why it form a lamellar structure, which consisting of parallel laths of iron and carbide Fe3. We always think of crystals as a perfect, right, but nothing is perfect in this world, including human beings or us. So therefore imperfection is invariably present in every material, and these imperfections have very important role in determining the material properties, whether it is a mechanical, physical, thermal or electrical or electronics or magnetic properties. These defects or imperfection will play a role, and imperfection can sometimes be introduced purposefully, or it then be present because of the processing by which these materials are made. So there are different types of imperfection presence: point defects, line defects, planar defects. Point defects means one small point or basically atom or number of atoms. Line means defects forms like a line. Planar means a 2D defects. Let us talk about each of them. So first one is a point defect. By point defect we mean a missing atom or set of atoms which are missing from the structure. So let us talk about vacancy. First one is a vacancy. You can see there is a regular arrangement of atoms, but this atom is missing here, you can see that. So therefore that is basically a vacancy, vacant site. So you can also have many vacancies present in the material. Surprisingly, vacancies are actually increases the stability of the crystal. Therefore vacancies are basically called equilibrium defects. At any finite temperature there will be finite number of vacancies present in the material. You cannot avoid them, because they reduces the free energy or energy of the system. How do they reduce? You can look at thermodynamic book and understand. I cannot discuss everything, but vacancies are considered as an equilibrium defect. Now in a crystalline metals you can have vacancies present anywhere, but when you talk about and basically ceramics, many of these ceramics have ion presence, because bonding is different in ceramics compared to metals, and therefore these ions cannot go away from the crystal or create a vacancy as usual like a metals. Why? Because if an ion is removed, the material will be positive charged. If a cation is removed, it will be vice versa, right. So therefore what happened, most of the cases both the ions are gone from the system. That is what is seen here. These big ions are basically anions, small ions are cations, right, like sodium chloride. Sodium is basically a cation, Na plus is a cation and Cl minus is an anion. Cl is a bigger atom, Cl has a much higher atomic number, Na is a smaller atom, is a lower atomic number, correct. That is why it is shown by a smaller circle, and Cl is shown by a bigger circle. So you can see one Cl atom, a Cl ion rather, and one sodium ion missing from the system. So it creates a pair of vacancies, and this will happen in pair only, because then only the ionic charge of the material will remain constant. Otherwise one of the ions are missing, material may be positively charged or negatively charged depending on whichever ion is missing from the crystal. Or you can also have formation of interstitial. Sometimes what happens, one atom like can go into interstitial positions. It is very one of the ions actually. It is very widely seen that in interstitial forms. Interstitial will not lead to any change of charge, because the ion is present in the material or the crystal. So therefore there is no loss of charge or no change of charge. Only thing is that interstitial is changing its location. Atom was at its crystal lattice position, but it is now moving into a interstitial positions. Interstitial position is basically a tetrahedral void, the one we talked about in case of diamond cubic structure, right. So this can happen here also. And third one is called a Frankel defect. In a Frankel defect, what happen? Okay, you can displace an ion, that is what very clearly can happen. So you can see there was a cation here, this cation has displaced there. Obviously this is not a stable configuration, both the ions are hitting each other, but it can happen because of many energy, thermal energy or something. So this is called a Frankel defect, and this kind of ionic pair is called a Schottky defects in the literature. So this is very simple. So this is called Schottky and this is called Frankel. these kind of structures, so these kind of point defects are very commonly seen in case of ceramics, and they can change in the ionic character of the material. In fact, this is sometimes used to create new materials for sensing, we know that. Now, you can have also line defects. This is nothing but a connected group of point defects. You have seen point defects is nothing but a missing atom or missing two atoms or atom going from one stable position to interstitial positions. Here in line defects, this group of atoms actually can form a line. They are connected and they can form a line in lattice structure. That is why it is called line defect. Most important line defects is dislocation. We all know dislocation, right? Whenever we go to play football or some game, sometime you can get your joints dislocated, whether joints on the leg or hand, it can get dislocated. Dislocation means is basically moving from its original position to some other positions, and then you have to go to a doctor to get it set in the actual position. So, dislocation is exactly like that. Let us talk about dislocations, how it is called. This one is basically a 3-dimensional crystal. You can see here atomic element of 3-dimensional crystal is shown, and what you see here at the middle of this plane, on the front plane, there is one extra row of atoms. This row here is missing, is not there. So, that means set of atoms, connected atoms formed a row, but it is missing from the front face of the crystal. So, this missing row can lead to an extra row of atoms at the tip of which there is an atom whose bond is not satisfied, and this is called an edge dislocation. It looks like an edge, and the symbol is like this. You can clearly see this is a slip plane, plane on which this extra row atom can move, and this is called extra row. That is why it is demarcated by this symbol. And now, this dislocation is very common in most of the metals and ceramics, widely seen, because it is easy to create, easy to move. Dislocation can easily move along this plane. This is the plane, right? Along this plane, it can easily move from this position to this position, this to this position, and then go to the surface. That is what happens. So, by application of the force, dislocation can easily move. While moving, it breaks only one bond at a time. That is why it is energetically favorable, easy to move, and this is widely seen in materials. You can also have another type of dislocation called a screw. Screw we know all of us, right? So, we can put a screw or a nut bolt. Screw is very easy to understand. Okay, all of you are probably used to a screw. You put it on a wooden structure and then use a device to move inside. It is exactly spiral, so atomic spiral within a lattice structure, but it is wrapped around imperfection line. That is what is the difference. It is wrapped around the imperfection line, that is why it is called a screw. So, if you look from one side, it will look like a screw. Like if you look from this side, it is looking like a screw. Atoms are like moving like a screw. So, I will show you much better picture here. As you can clearly see that this is basically projection of the atoms on a screw dislocation. What you see from this side is basically a screw moving, right handed screw moving inside the material. You can see the screw. This is how it is. Okay, you can follow me and see that. This is what it is, and this it ends on the surface. So, atoms, if you plot the atomic location of the atoms above the plane and below the plane of a dislocation, they look like a screw, and depending on which way you are looking like, it will look like a left handed right handed screw. So, here if I look from bottom or from my side, it is looking like a right handed screw. It has a pitch also. So, every screw has a pitch, you know that. So, that is how actually atoms can be displaced. So, by simply moving the screw, we can move inside the material or inside something. Similarly, we can apply force and the dislocation can move inside the material. The screw dislocations are also widely seen. In fact, most of the dislocations actually are mixed structure, they are not screw or edge. You can also have a planar defects, or what is called a imperfection that can extend in two directions. As you have seen, this was imperfection which is basically extending one direction. In fact, this is the best example, the edge dislocation. This is extending along a line, it is not extending along two directions. Screw is basically along a line, if you draw a line and through this is, but it is not perfectly, like it is an extended object. But planar defects are actually extended in two directions to form a boundary. That is why it is called planar defect. Most important planar defect is gain boundary, which I have shown you in the couple of last lecture. Here you see these are the gain boundary, this is the planar defect, right, this is the gain boundary, where two grains, one grain is falling on other grain, that is why it is form a boundary, right. This boundary is grain 1 and grain 2, they are falling on each other. Depending on how the atomic structures are following each other, all kinds of gain boundaries can be formed, but fact is this is a boundary formed by two grains, and this is a planar boundary because extend this boundary is basically extension. I will show you later extension of in the two dimension x and y. So let us go back to twin. So what is a twin basically? You know, twin is something which leads to huge amount of displacement. It is shown here. You can clearly see this plane. If I look at this plane, this part of the crystal and this part of the crystal, they have mirror image. Same thing here. You can see here this part and this part of the crystal have mirror image along this plane. If you put a mirror here, they will look like a mirror image. So twin leads to extensive deformation, large scale deformation possible. Unlike dislocation where you can only have, you know, only a small domain region near the dislocation getting atoms are getting displaced or distorted locations are possible. Here you have a wide region in which atoms are getting displaced. That is why twin planes actually very important, and most of the HCP metal, hexagonal close packed structure metal like zinc, magnesium, they undergo deformation by twinning, and this is very important because if you want to deform material to give a particular shape, you need to deform it by under proper conditions, and that is why twinning is very important. This is a real microstructure, obviously colored for your purpose. You can see the twins. This is a twin line, this is a twin line. There are many places. This is a twin line. Okay, this is a twin. So twins actually look like a lenticle shape inside a grain. Then if I have a grain, twin look like lenticle shape like this. That is what a twin look like. You can see under microscope and also understand. I know many of you would have already seen, because once you have done lab using different kinds of material like copper. Copper has annealing twins present, or if you can see in zinc is hexagonal close packed structure, it can also show all kinds of twins. So let me just wrap this part up. So by now you know the nature and properties of material depends on what type of atoms it consisting of and how these atoms actually arrange inside a material, what is called internal structure of the material. So one is the chemistry. Chemistry is the type of atoms are present in the material. Second one is that how we arrange the material inside the structure, and third one obviously you saw the defect structure. So we can actually say that internal structure means arrangement of atoms or molecules, or they are defect structures, and depending on the scale of observation or the optical microscope or SEM or other TEM or things, different kinds of internal structures can be observed, and these structures can be obviously microstructure, substructure, crystal structure, or even nuclear or electronic structures can be also probed. So all these things together, obviously you do not need to learn everything. Most important thing you have to learn is how the atoms are distributed, what kind of defect structure is present, and obviously microstructure, grain structure. That is what you need to know very well in order to understand this. So with this we stop first part of the lecture, and in the next part we will talk about more of engineering materials and how they are important. Thank you.